Hello everybody. With this presentation I will show you some of the RadioAstron results from the AGM Polarization Key Science project led by Jose Luis Gomez, and in particular the observations conducted on 3C273 during the first year of the project. As you probably know, 3C273 was the first discovered quasi-stellar objects identified by Martin Schmidt in 1963. Since then, thousands more quasars were discovered, and many are regularly targeted by monitoring VLBI programs like Mojave and VLBA View Blazer. The first space VLBI observations on 3C273 were performed during the 90s in the context of the VSOP mission with an 8-meter diameter orbiting radio telescope plus VLBA on Earth. It could be possible to reach a resolution of 2 times 0.4 milliarseconds at 5 gigahertz and detect a double helical structure consistent with Kelvin-Helmholtz instabilities along the jet stream. The RadioAstron AGN survey targeted the 3C273 at 22 gigahertz in 2012-2013, measuring a record brightness temperature of 10 to the 13 Kelvin above the inverse Compton limit. In 2014, 3C273 was observed again during the AGM polarization KSP at 1.6 and 22 gigahertz. The 22 gigahertz observations were supported by a truly global ground array, including VLBA, EVN, LBA, quasar, GBT, and Kaliazin. The experiment was designed to reach 9 Earth diameters. However, the low source flux limited the detections on space baseline to about 1 Earth diameter. Indeed, the overall single dish monitoring confirmed a 50% drop of flux since 2010. The final map at 22 gigahertz had a resolution of 0.37 times 0.29 milliseconds, and we could estimate the brightness temperature for the core region via model fit and compare it with the extreme one obtained during the AGN survey just 1 year before. The obtained values for the 3 components in the core region were found to be below the inverse Compton limit and also the equipartition value, confirming the exceptionally low activity state. It's important to stress that we had the same instrumental setup of the AGN survey, suggesting that the brightness temperature really had a drop of 2 orders of magnitude in only 1 year. We further investigate this difference and we performed a jet kinematics analysis of the inner part of the jet using the VLBA View Blazer at 43 gigahertz and considering all the epochs between 2012 and 2014 in order to cover both the AGN survey observation and ours. The angular resolution is very similar to our RadioAstron image, and we found that the core underwent a radio flare at the beginning of 2013, after which a new component was ejected. The stationary component increased its brightness temperature just after the core, and after that, the new component called D5 and these plots became visible. This suggests that the stationary component is most probably a recollimation shock, increasing its flux while the new component passes through it. The ejection of the new component is subsequent to the AGN survey epoch, suggesting that it was upstream the core during those observations. This would imply a size lower than 14 microseconds, consistent with the one estimated for the component responsible for the extreme brightness temperature detected in 2013 of only 26 microseconds. These results were published in the second paper of the Polarization Key Science project in 2017. A few months after the 22 gigahertz observations, we observed 3C273 at 1.6 gigahertz. This time 11 ground antennas were involved, including LBA, Quasar, RTB, and Usuda. At this frequency, we could count on a larger flux from the source and get good detections up to 5 Earth diameter. We could reach a resolution of 1 time 0.58 milliseconds that is unprecedented at 1.6 gigahertz. As you can see in the image, an edge brightness structure is visible, resembling a double helix. This was never detected before in 3C273. We decided to further investigate this pattern, performing an analysis of the transverse profiles along the jet. To do so, we considered the jet axis estimate from the Mojave stacked images at 43 gigahertz, and then draw almost 400 profiles along it. In the central image, you can see some of the most representative profile found. As you can see, a persistent double peak structure is visible along the jet. These results encourage us to compare what we were seeing at 1.6 gigahertz with the 4.8 gigahertz observation performed in the same period in the framework of the strong AGN Key Science project. This could get detections up to 3.3 Earth diameters, corresponding to a beam of 0.8 times 0.4 milliseconds, and a comparable RMS. As you can see in the right image, a structure resembling the spine of the jet is visible, with a curvature coherent with the 1.6 gigahertz one. Indeed, a superimposition of the two images reveals a strong complementarity. On the left panel, you can see the 1.6 gigahertz image in contours and the 4.8 gigahertz one in colors. As you can see, the latter traces the spine of the jet, while the 1.6 gigahertz one the edges. On the right panel, you can see the stacked image from Mojave at 43 gigahertz in contours, overlaid to the 1.6 gigahertz one from RadioAstron, showing how, with the exception of the first few masks, RadioAstron observation traces the edges of the jet structure. To further test this, we integrated the flux density along 300 fluid lines for both RadioAstron images and plotted the resulting total profile that you can see in the central panel. The blue line represents the profile from the 1.6 gigahertz image, while the red one, the 4.8 gigahertz profile. The two are complementary and confirm a double peak structure at the lower frequency, consistent with the jet edges, while a single peak at the higher one, consistent with the jet spine. It is important to stress that the detection of this structure for the first time in 3C273 was only possible thanks to the extreme resolution accessible with the RadioAstron observations. The spectral index map, built with the two RadioAstron images, shows a steep spectrum for the limbs, while a flat inverted one for the spine, as expected. These results have been submitted to ENA and will be published soon. So concluding, RadioAstron 22 gigahertz observations performed during a low activity status revealed a core brightness temperature 2 orders of magnitude lower than the one estimated only 1 year before by the AGN survey program. From a kinematics analysis, we found that a new component was ejected 2 months after the record brightness temperature measured in 2013. So what we can learn is that the access to extremely long baseline and thus resolution does not systematically imply brightness temperatures larger than known physical limits. In other words, the brightness temperature estimates are still driven by the status of the source and not by instrumental effects alone. Thanks to the unprecedented resolution of 1.6 gigahertz that provided by RadioAstron, we could detect a limb brightening along the jet, while at 4.8 gigahertz we could see a spine brightening. Hints of a double helix are visible at both frequencies, although with a different pace. Overall, the observed structures can be explained in terms of a jet stratification in velocity, a differential Doppler boosting, or steep energy stratification across the jet with, or again, a helical magnetic field. Future magneto-hydrodynamical simulation will try to reproduce the observed structures and quantify the physical parameters necessary to explain that. If you want to know more about the RadioAstron imaging programs, you can have a look at the review we published past year that collects the main results from the 3 AGN imaging key science projects. Thank you very much.